This is Fundamental Problem 11 from Chapter 17. The uniform slender rod has a mass of 15 kilograms. Determine the horizontal and vertical components of reaction at the pin O and the angular acceleration of the rod just after the cord is cut. So because they ask us for the horizontal and vertical components, I call the components OX and OY, but we're going to use Newton's second law with the normal and tangential components, so I'll have to relate the x and y components to the normal and tangential components. So I'm going to say the x component's going in the positive x direction and the y component's going in the positive y direction. Okay, this problem, at least the beginning of it, is very similar to Fundamental Problem 9. So we're going to sum up the moments about point O and set that equal to the moment of inertia about point O times the angular acceleration. So the first thing I have to do is find the moment of inertia about point O, and I'm going to use the parallel axis theorem for that. I have a slender rod. If I go to the back cover of the book, for the slender rod, about the mass center, the moment of inertia is 1/12 ml squared. So I have 1/12 the mass times the length squared. The length is 0.9, just like it was in Fundamental Problem 9. The similarity doesn't end there. In Fundamental Problem 9, point O was a distance of 0.3 meters from the left end of the rod. Here in Fundamental Problem 11, point O is 0.3 meters from the right end of the rod. Both rods have a length of 0.9, which means the distance to the mass center from the end of the rod is 0.45. And since this distance is 0.3, just like it was in the previous problem, D is equal to 0.15. That's 0.45 minus 0.3. So for the parallel axis theorem, I get this plus the mass of 15 times D squared, which is 0.15 squared. And that is the parallel axis theorem from equation 17.4. And this gives us for our moment of inertia 1.35. So now I can go back and do the sum of the moments about point O. And I don't include the forces which are acting at point O, so I'm just looking at the force of gravity which is acting downward. That's m times g at a distance of 0.5 from point O, and that would cause rotation in the positive direction. So this is the mass times g times the distance of 0.15 is equal to the 1.35, which I have for the moment of inertia, times the angular acceleration. Therefore, putting in the mass of 15 kilograms and 9.81 for g, I get an angular acceleration of 16.35 radians per second squared. That was something they asked me to find. You can do the calculation on your own to check to make sure that that is correct. And it's positive because the angular acceleration is going in the counterclockwise direction. So after doing that, I can look at Newton's second law. So I'm going to do that using these equations here for the normal and tangential component. So I'm going to copy those down. I have the sum of the forces in the normal direction is equal to the mass times omega squared times rg, and the sum of the forces in the tangential direction is equal to the mass times the angular acceleration times rg. Now, they asked us to do this just after the cord is cut. At the instant the cord is cut, the angular velocity is equal to 0, which means when you sum up the forces in the normal direction, you get 0. And if you look at the forces which are acting in the normal direction, well, first we have to decide what the normal direction is. So the normal direction, if you go back to our figure from the beginning of this section, remember normal is always pointing in towards point O. So if you look at point G here, this is the normal direction pointing towards point O. So this is the normal direction, OX, is the component which is in the normal direction, and it doesn't matter whether it's positive or negative because it's 0. So the x component is equal to 0. Okay, and then my tangential component, if I look at my diagram here, the point G is going to start moving this way. So this is the tangential direction. So M times G is pointing in the positive tangential direction. So when I sum up the forces there, I have M times G. And then for the tangential component of this force here, well, tangential is downwards, and the y component we said was pointing upwards. And it could be that the y component turns out to be negative. But we're going to say if the y component is pointing upwards, that's the opposite of the tangential direction, so that's minus OY. And this is equal to the mass times the acceleration times RG, that's the distance between O and G, that's 0.15. And so I know the mass and I know the angular acceleration, so I can solve for the y component. So if I bring this over to the other side and then bring this over to this side, that's the mass times G, so 15 times 9.81 minus 15 times my angular acceleration of 16.35 times 0.15, and that gives me 110.4 newtons. And because that came out positive, that means it's pointing upwards, because I said this was pointing upwards. So if it turned out negative, if OY turned out to be negative, it would mean it was pointing downwards. Okay, so that concludes fundamental problem 11.